Hi everyone, this is Mr. Chu. I'm going to cover 9.3 today. 9.3 is a huge topic. It is going to comprise of 3 parts. And the first part I'm going to do is on double slit interference pattern and its modulation by the single slit. I'll explain what it means. The second part will cover on diffraction grading, and the last part, which is going to be on thin film. That's going to be the one that is slightly different from the other two. So let's begin with the two source interference pattern. I think I might have gone through this with you, but just a recap. So if you've got two sources over here separated by distance d, and imagine that the wave goes out in all directions, and we consider one point where they meet on the screen, and say for example this is theta over here. Now let's clean this diagram up a bit and so that it only has these two rays over here. And this is theta. The place where they meet on the screen is L, and this is D. So if we take a careful look, we can see that this is the additional distance traveled by this wave over here. Now if this is theta over here, this will be theta 90 minus theta, because this is 90, and therefore by some simple trigo, that angle over there will be theta as well. So this length over here divided by d will be sine of this. So path difference divided by d will be equals to sine theta, and path difference is equals to d sine theta. So that's the path difference. And we must remember, you must keep in mind that this distance over here is in the order of meters usually, and this is in the order of 10 to the power minus 4 meters, which is about 0.1 mm. So what's the implication? The implication is that this angle usually we consider it to be really small, close to the center. So when the angle theta is small, what happened is that we can actually approximate it to tangent theta. Why so? Let me explain it quickly. So if you've got a right angle triangle, this is opposite, this is adjacent, this is hypotenuse. Sine theta will be equals to opposite over hypotenuse, whereas tan theta will be equals to opposite over adjacent. If the angle theta is really small, this will be approximately this, hence this will be approximately equals to this, because h and a will be about the same. So therefore we can say that this is, I should use the sign approximately. So this is d tangent theta, and d tangent theta is going to be equals to, let's call this y. This is going to be y divided by L. And remember, for constructive interference, this has to be equals to n lambda. Now what does this mean? It means that y, which is the positions where there is constructive interference, is going to be nl lambda upon d, which means that the various positions that you can find constructive interference will be this, and 3l lambda upon d, and so on and so forth. So delta L is equals to L lambda upon d, which is the separation between the bright regions. And I think I went through this with you, that you need to know how to sketch the pattern. They are evenly bright and evenly spaced. So between this and this, it will be L lambda upon d. Between this and this, it will be L lambda upon d. And I went through with you the phasor diagram method, remember? The path difference over here is equals to d sine theta. So the phase difference is going to be 2 pi d sine theta, which is delta x upon lambda. And we represented the wave from this to be over here, a being the amplitude, and the phase difference, this one is represented in the diagram by this, and it's almost like a vector sum. So the A resultant, and this is A, is equals to 2 times A cosine phi upon 2. And therefore, if we were to take the intensity to be proportional to amplitude square, so the amplitude will be 2A cosine phi upon 2 squared, it will be 4A squared cosine phi upon 2 squared. And if you were to plonk in the phi that we worked out just now, it will be cosine pi upon lambda d sine theta squared. The 2 goes away because it is divided by 2. Now, take a look. The IR over here will be maximum when this thing over here is either equals to 0, when this thing is equals to 0, pi or 2 pi. And therefore, if you work out the d sine theta will either be 0, which is the central maxima, Or you can work out d sine theta to be equals to lambda, which is, because let me just show you one. So pi is equals to pi upon lambda d sine theta. So if you cancel out the pi, you put d sine theta equals to lambda, which is exactly what we were doing over here just now. The d sine theta, which is the path difference, must be equals to n lambda. So this is a fuller derivation, which you don't need to know for IB, but it's always good for you to have this additional tool to be able to explain fully mathematically how the intensity and why the intensity looks like this. However, is this how things look like in real life? Fortunately or unfortunately, no, it doesn't look like this in real life. So how does it look like in real life? This is what we're going to discuss. Now remember that what's the assumption that we have about the intensity from each single slit for the two slit interference pattern to have the same intensity for the maximus? Now we assume something which wasn't obvious, but we did assume something, that the intensity due to source 1 is flat, source 2 is also flat. Remember why so? This is the reason why if we have a minima, by the way, the height of this is relative, so it doesn't mean that S1 and S2 is more than the resultant. So it's just telling you that S1 and S2, we assume it to be constant, to be the same. So what we have over here is the reason why we have all these minimas at 0 is because we assume that the intensity or the amplitude due to each source are the same. That's why they can cancel out perfectly. Alright, and the reason why they're the same throughout is because the amplitude due to each wave from S1 and S2 on the screen, they are the same. However, is it the same? Now remember, we went through single slit diffraction pattern, that if we have S1, S2, do keep in mind that these two sources are really close to each other. I'm giving them this physical separation so that you can see these are two different sources. Otherwise, if I put them too close together, you see it as one single spot. So in real life, each of the source or each of the slits, right? Each of the slits, remember, they behave as a source. So each of the slit has a finite opening over here. And because of the finite opening, remember that any wave passing through an opening, it diffracts. So the intensity is not this one. It is not flat. It is actually like this. Remember, this is very much smaller than this. So each of the slits over here produce a pattern that looks like this. Both S1 and S2, remember, they are very close to each other, so their pattern actually overlaps on top of each other. So instead of this, each of them produces a wave that looks like this. I'm not even talking about interference yet. I'm just talking about the intensity of wave of the light from each of the source overlapping. That's not taking into account interference yet. Now, if we take into account interference, can you therefore see that if we just combine the two profiles into one, can you see that at this point, the intensity from each of the wave is going to be really strong, so you got a very strong maxima over here. However, if this is the position where this is 0, this is L lambda upon D, remember this must be the position of another maxima. So instead of having a maxima that is as high over here, it only has a maxima this high. Now imagine another point where it's 2L lambda upon D, where there's supposed to be a maxima here, it is going to be much lower. So therefore, we have a series of maximas that are of different intensity. That's why if you remember one of the pictures that I show you about double slit interference pattern, there's a bunch of fringes and then it goes off in intensity, and then there's another bunch over here. So these are the other maximas forming this bunch over here. So what do we say about this? This is basically the two source interference pattern modulated. The word used is modulated by the single slit diffraction patterns profile. Alright, so this is something that you need to know, and there's actually more information we can pull out of this pattern. What do I mean? Remember that this sine theta is equals to lambda upon D, Okay, I'll use another one. I'll use big D, which is the diameter of the opening over here. It is not this D that we used just now. It is this D over here is the diameter of the opening, or the size of the opening. Whereas this one, remember, this separation between the two maximas of a double slit interference pattern. So let's bring this up. Single slit, the first minima position is lambda upon D, and the separation between the maxima is where, if you've got two slits, is where path difference equals to d sine theta equals to n lambda upon n lambda. So therefore, at the positions where you have maxima, it is sine theta equals to n lambda upon d. Be very careful, this is slit separation, whereas this is slit width. Alright, so why is this important? Say for example, if there's supposed to be a fourth maxima over here, 1, 2, 3. This is the third maxima over there, but the third maxima cannot be seen. The third maxima of the double source interference pattern, first, second, third, coincides with the first minima. What sort of information can we pull out? So if the third maxima of the two source interference coincide with the first minima of the single slit diffraction pattern, we can say that this theta, which is lambda upon big D, this is single slit, is equals to the third lambda upon D. Why third? Because I mentioned it's a case, it's a scenario, it's not always the case. It depends on question. So if it is equal to the third maxima, I can cancel away the lambda. I can say that D is equals to 3D. So it means that the slit separation is equals to 3 times the slit width. So by just counting the number of maximas I can see up to the point where I can no longer see the maxima, I can actually get an approximate gauge of the relative size or magnitude of the slit width and the slit separation. So this is how you can pull the more information out from this diagram over here. Alright, so this is basically about the two slits interference pattern and the two slits interference pattern modulated by the single slit diffraction pattern. So that's all for this portion over here. I hope you have a better understanding of two slits interference pattern and why I did single slit diffraction pattern, then I come to 9.3, because there is some overlap and you need certain ideas from 9.2 to explain what you see in 9.3. Alright, so I hope you understand this better. I'll go on to part 2, which is on diffraction grading. Thank you.